Hello. This lecture will cover pages 35 through 37 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Resistive Circuits, Chapter 2F, Delta and Wye Networks. We're going to start by looking at page 35, and we're going to discuss Delta and Wye configurations. Using the knowledge you've learned so far, how would you calculate the total resistance of the circuit shown below? Let's take a look at that circuit for a minute and tell me, how could you calculate the total resistance looking into that circuit so you could divide it into the 24 to get that total current IT right there? Well, if you look at the circuit, the 150 ohm resistor and the 50 ohm resistor are not in parallel. They might look like it at first glance, but they're tied together at this end, but this end and this end are not tied together because there's a 100 ohm resistor in between. Same thing down here. This 300 ohm resistor and this 250 ohm resistor are not in parallel. They're tied down here, but to be in parallel, this point and this point have to be the same point. There's a 100 ohm resistor in between. This type of circuit is called a bridge, and special techniques must be used to analyze it. You can't use the tools up to this point. That leads us into a delta configuration or Y configuration. Delta and Y configurations are very popular in power, in instrumentation. We're not going to get into that in this course. That'll be future courses. But for this course, I want you to be able to recognize elements that are configured like this. Obviously, you could see the delta, inverted delta, are referred to as a delta configuration. And we're going to label them R1, R2, and R3 with points A, B, and C. These point references for the formulas are going to be important. You can't put A, B, C. The formulas won't work. But for this author, that's point A, this is point B, this is point C. R1, R2, and R3. And a Y configuration. It's an upside down Y, but nevertheless, they refer to this as a Y configuration. There's your A, there's your B, there's your C, and this is RA, RB, and RC. The delta configurations use the 1, 2, 3 convention, and the Y configurations, we're going to use the small a, the small b, and the small c configuration. So if you look up here in this circuit, clearly you can see a delta configuration here between this and this and this resistor, or a delta configuration here between this one, and this one. If you could replace this delta configuration with the Y configuration, in other words, replace this point A, this point B, and this point C with this configuration, once you make equivalent calculations for resistances, you'll see that you can use your techniques to solve for total resistance, because things will be in parallel in series at that point. You'd have to replace this circuit here, this delta, with the Y up there, or the bottom one. You could replace the bottom one with the Y once you make the calculation. How do you make the calculations? Delta to Y and Y to delta transformations. This is something you just be aware of. Using the diagram below, and what I do is I use this diagram. If you use this diagram, you can see these equations real easy. Notice there's my point A, there's my point B, and there's my point C, and I drew the delta, and inside the delta I drew the Y, and I labeled the resistors R1, R2, and R3 for the delta, and RA, RB, and RC for the Y. When converting from delta to Y, let's say you have the delta, erase that in your mind and just look at that delta. You have a value for R1, you have a value for R2, and you have a value for R3. But what you want to do is you want to get rid of that and just make a Y out of it. Well, here's the equation for it. And you don't memorize these equations. You'll never have to. Future instructors, or if you're in industry, you'll just go to an equation and you'll use it. But how do they come up with RA? How do they get an equivalent resistance for the delta starting with RA? Well, if you take a look, it's R1 times R2. It's the two resistors that meet at this point at RA, at point A. So it's in the numerator, it's R1 times R2 divided by the sum of all the resistors. Once you see that, look what RB is equal to. You don't even have to look at that formula. You know what RB is going to be equal to. It's going to be equal to R2 times R3 divided by the sum of all of the resistors. And what's RC going to be? RC is going to be equal to R1 times R3 divided by the sum of the resistors. So if you knew an R1, R2, and R3, you could replace it with a equivalent Y. What about converting from Y to delta? Look up here at the top, and I want you to look, how do they get R1? They want to calculate R1. Now you have a value for RA, RB, and RC. We want to erase that and put in a delta. Well, R1 is equal to RA times RB. Let's see how they're getting that. R1 here is equal to RA times RB It's just the product of each of those resistors in the numerator. It's RA times RB, it's RB times RC, and it's RA times RC. And you divide by the resistance that is opposite the value of R1, if you're looking for R1, which would be RB. So how do they get R2? Without even looking at the formula, how are you going to get R2? Well, it's the product of all these resistances again in the numerator, but you're dividing by RC, the opposite resistor. And how do you get R3? Don't even have to look at that. As long as you know it's the product of these Y resistors, and it's going to be divided by, don't forget, we're trying to get R3 now. It's going to be divided by RA, and that's what's in the denominator, RA. Let's see if you can use these equations. If you look at example 225 in your textbook, I'll show you what I mean. Good example. We're only going to do one of these. So if you take a look here we have a circuit, and they want you to calculate maybe the total source current here. Well, you can't use normal techniques here. You just can't use normal techniques because nothing's in parallel or in series. But if you could label this point here, I mean, we could label these points. You put a point there, you label it. You put a point there, and you label it. And you put a point there, and you label it. Well, that's this point here, and that's this point here, and that's this point here. So all we're doing is taking these resistors, this delta, here, here, and here. This is a delta. These three resistors at the top. And we're replacing them with the equivalent Y. And once you do that, the 4K gets put back in, and the 9K gets put back in. Look at that circuit now. The total resistance of that circuit is this 6K in parallel with that 12K. And you add the 6K in series. You can get the total resistance at that point. You can even do it in your head. I mean, if you take, let's see here, 6K in parallel with 12K, 6K in parallel with 12K is 4K. So this whole thing here is 4K. 4K in series with 6K, that gives you 10K. Take 10K and divide it into 12, you get 1.2 milliamps. Done. Take a look in, we're looking over here on page number 38 of our lecture notes, and I want to look over problem 2, 123 at the end of chapter 2. Let's take a look at it once here. Let's look at this problem here. Find it in your version of the textbook. Looks like this. Do you see a delta configuration there? Well, I see two of them. I see two delta configurations in that circuit. I see a delta configuration up here, or I see a delta configuration down there. But what's unique about the delta configurations? Well, this resistor right here, that resistor right there, and that resistor right there are non-existent. That resistor is 0 ohms, and that resistor 0 ohms. So you can look at this circuit, and you could convert it to a Y, either this to a Y, and I showed you a Y in there so I could erase these two. Or you could do it down here using that resistor as 0 ohms. But you don't have to in this case. Why? Because even though that's a delta drawing, the way they have it there, the 6 ohm and the 3 ohm are in parallel in this circuit. Look, they're both tied together on that side, and this is a common point up here because that's 0 ohms. That's 6. And that 3 is 18 over 9. That's 2 ohms. You can just draw a 2 ohm resistor there. Same thing down here. So this circuit would be redrawn with a 2 ohm resistor gone down in series with a 2 ohm resistor. That's the first step in this circuit. You don't have to use delta to Y transformations here because that value is 0. If you did, you'd get the same answer. You might want to try it. And that concludes this lecture.